Hello and welcome to this repair tutorial, and today we're going to look at a Denon PMA 510AE amplifier. And just out of interest, there is also a model 710AE, which is a slightly more powerful version than this unit. In terms of power output, RMS delivers 45 watts per channel into 8 ohms, but this will increase to 70 watts per channel if you connect 4 ohm speakers. And then frequency response comes in at 20 Hz to 20 kHz. And total harmonic distortion is 0.7% for 4 ohm speaker load, but that will actually improve if you have the 8 ohm speakers connected. Now this amplifier does have a moving magnet phono type input circuitry as standard, so your input sensitivity there is 2.5 millivolts, and then for all other inputs it refers to these as the all line inputs, and your maximum input sensitivity there is 100 millivolts. And then in terms of dimensions, width of the amplifier comes in at 434, height 121, and then depth goes to 307 millimeters. And then the weight of the amplifier is approximately 6.5 kilograms. Now the unit itself, when you look from the front, it is a good looking amplifier. And I know for many of the listeners out there, there is a huge loyal following for Denon amplifiers. And in terms of operational performance, this amplifier doesn't come short. It really just delivers a distinctive sound, very deep and rich. And from a repair point of view, I do repair, full range of amplifiers from whichever make. But I think I've repaired, quite a lot of these units over the years, and you do kind of get into them and you sort of get to know, how Denon have laid out the boards and the circuitry and everything else. But I'm quite a fan of these amplifiers. Now it does come with a remote control as well, so again, if you need to, you can operate the unit from the front fascia or alternatively via the remote. And then what you have is the ability to have 2 sets of speakers connected, so speaker set A and speaker set B, or 1 and 2. You also have a tone defeat, and then this bypasses the tone control circuits, and also a loudness switch, and this is very common on the Denon amplifiers. And then you have individual bass, treble and balance control, of course volume, and then the input selection, just a rotary encoder. But it's sort of nice when you operate the unit. What you will find is, even if you select via the remote or from the front fascia different input channels, what you'll hear is the speaker protection relay de-energize and then re-energize, and that's not uncommon. Many manufacturers use that just really to effectively mute the speakers when you're changing inputs, which is kind of like a nice feature. So let's sort of talk about what the issue was with this amplifier when it came into the workshop. Well, what I'm showing here is the power input board, or also sometimes referred to as the standby board as well. These circuits are always powered, and what it provides is the necessary voltage to the microcontroller. But on this board as well, you'll see that there are 2 protection fuses. The one that is of interest here is F901. Now F901 is rated at T, or time delay, 2.5 amps, and then you can see the other fuse. Now when you remove the top cover, the issue initially was that the owner of the amplifier reported that it was in protection mode. And of course the reason why that has happened is because one of those fuses has failed. So when you have this situation and you remove the top cover plate, the first place that you need to look at are those 2 fuses there. And what you can see is that the fuse wire internally is vaporized. So that tells you at some point in time there has been excess current drawn. And when you sort of look at it, from experience, you know that it's not just a power surge that has caused that. It indicates that there is a more serious issue requiring components to be replaced then. So the next sort of thing that I want to sort of bring to your attention is what typically is the nature when this fuse fails. Well, sadly, in virtually all cases, what you will find that either the left channel or the right channel output transistors will have failed short circuit as a minimum. Okay, and depending on which fuse fails will indicate which channel has actually failed. Now what you'll also or what's also important as well is that with this amplifier, it didn't fail because of something that the user did. And the thing that I want to sort of show you now in the video is you're looking at the driver transistor for the output stage of the amplifier, and I've sort of circled it here, and what you can see is that one of the component leads of that transistor during manufacture was not soldered. So how the board is designed, with no solder on there, you just have these cuts, and with the power output transistors and the driver transistors, the leads protrude down, and then during manufacture they just bend the leads over, cut them to a particular size so they don't interfere or short to any forward facing components, and then the solder is run on top of there. How this unit has continued to run is a bit of a mystery, really. I think it's just a case where it was just making enough contact, and then at some point in time it didn't, and what has happened is you see a catastrophic failure of the output channel. Now, there's always a balance between the thermal fuse or the time delay fuse triggering and the destruction of components. So sometimes when these amplifiers fail, you may only need to replace the output transistors. The destruction of the components have gone no further than that. But the nature of this failure meant, as I said a moment ago, it was completely catastrophic. So that meant that multiple components in the amplifier output stage have failed. So the next thing I'm bringing to your attention here is really the extract of the left channel circuit diagram. And what I'm showing you here is a couple of things, but one of them I'll come back to later, which is around the bias setting. So you can see that it wasn't just the output transistors. You can see that we had the failure of the emitter resistors, and this is R351 and R349, and these are 0.22 ohm, and they're ceramic type, and they're rated at 5 watts. And then also as well, on the circuit board, which is very, very close to the driver transistor, which is Q317, you have R337, which is an 820 ohm quarter watt resistor. It's actually smaller than quarter watt, but I've just put nominal quarter watt because if you are going to replace that component, you'll normally fit a quarter watt, probably, or maybe an 1/8 watt is probably the smallest you can go down to. And then what you find are these bias components as well. So within the amplifier you have the D311 and also D315, and the part number is 1SS133M. Now if you try and source these, you may have difficulty doing that, but those diodes are no more than 1N4148s. So you can use a 1N4148 500 milliwatt signal diode to replace D311 and D315. And then D309 and 313 are 3 volt 500 milliwatt Zener diodes. So that's quite easy to sort of source and then to replace. With regard to the Sanken outputs, this is Q319 and Q321. Sadly, probably about 6 months ago, these components went to last time buy and are now no longer manufactured. So the difficulty is that if you're looking to repair them or repair the amplifier, you'll need to source genuine originals. And I've mentioned this so many times in the repair tutorials. Just be very aware that the marketplace is flooded with counterfeit components, and if you go out and then source them, just be aware that they should be Sanken, but they're all also what we term as Darlington transistors. That means that there is 2 transistors mounted within the same case, which is designed to deliver more power for the single component. And because of the counterfeit, they may look physically the same, but you may not even find that they are indeed Darlington devices. So just be careful, when you're looking to source those. And then the other component which failed, and I'll sort of mention it briefly, is Q317. The Q317 is mounted onto the heatsink, and that's a 2SC311A, and that's the volt or the actual driver transistor then for the output stage. Now that's quite a lot of work to do, and what I would also sort of highlight as well, and I'm sort of showing the different stages here with the components removed and then with the components replaced. the circuit board foil track, or the copper track, is very, very thin. You know, and you can find this with some makes of amplifier. I don't know if it's a cost cutting thing, but the amplifiers are using a lead-free solder, and also as well the components are bent over. So you got to kind of be careful here, because you've got to heat up the lead-free solder and then try and desolder it, but then at the same time lift up the component lead which has been bent over. And because these tracks are very, very thin, it's easy for the tracks just to lift up with really a modest amount of heat. So really what I'm saying to you is you need to just take your time on that, right? Because some of these components are very small and some of the PCB tracks are very close to one another. So it's not difficult, shall we say, to damage one of the tracks, or maybe, for example, accidentally get a solder bridge. So just take your time, all right? Don't sort of rush that. Otherwise you'll be in the position where maybe you've damaged the track and then you have to do, you know, some repair work. And like I've said in previous repair tutorials, what you need to do is just check your work after. Just, you know, just take that extra bit of time, make sure that everything is all good then. So once that was done, what do you do next? Well, what we do next is that, of course, after we replaced F901, is to power up the amplifier then via the gimbal tester. Now, I've mentioned again on other tutorials, just take a bit of time after you replace the components in the output stage to just do more measurements. All right, so drop your meter onto resistance and just meter around that output stage, just to make sure there's nothing in there which I would term as like silent killers. And when I use the word silent killers, I'm referring to components which physically look fine and you think that they're great, but actually they have failed. And one of the components that you would need to check here is VR31, for example. VR31 is the 500 ohm bias trimmer, and because we had failure of Q317 and we also had failure of R337, just desolder that bias trimmer and just check it with your meter, right? Bias trimmers can go open circuit when output and driver stages fail, and the last thing you want is to do all that work and then replace, and then you power it back up and then you have another catastrophic failure. So you power up the amplifier by the dim bulb tester, and that was done, and the dim bulb didn't light bright at all, and then probably about 5 seconds what you hear is if it's selected from the A or B push buttons on the front, you should hear a click, and then that's the speaker protection relay coming into operation. And then what I'm looking for is it makes sure that, for example, that there's no high DC offset on the output channels, and then I'm also then looking to set the bias. Now there was a second issue on this amplifier which I'll talk to you about in a moment, because we'll go back to the circuit diagram. But before we do that, I just want to talk to you about what you do when you're going to set the bias, because this second fault you would not have been able to identify it until the amplifier was operational. So once the amplifier has cleared its protection mode and it's then running, the next thing that I'm interested to do here is to set the bias. And it's very easy on this amplifier. What you have are connections on the board, and you can see here for the left channel it's CM31, and you're looking at pins 1 and 2. Pin 2 is not used, and you just insert your multimeter probes into there, and then you set your volume control to minimum, no speakers connected, no input signal, and your balance, tone and treble control all at mid position, and then leave the amplifier probably running for about 15 minutes. Okay, that just makes sure it just warms through. Stable environment, you don't have any sort of drafts taking place, and then you adjust that until you read 10 millivolts on your multimeter. And there's a small tolerance here. The manufacturer will give you 0.5 millivolts. Either side of 10 millivolts has a tolerance. Now with the presets, it's not a multi-turn, so these things are sometimes a little bit twitchy. So just be very, very careful, you know, just take your time. If you're finding that it's probably not as smooth as it could be, depower the amplifier and just spray into there, for example, some deoxide, and just rotate that preset backwards and forwards multiple times, and then return it roughly to the position to where it was originally, and then put your power back on again, let it warm, and you should find then that there should be no issue, you know, to bring it then to 10 millivolts, pretty much bang on. And remember also as well, check the other channel, all right? Because the amplifiers have been in service for many years, it's not uncommon that the bias value will drift, and that's perfectly normal, okay? Now, let's come back to what was the second issue with this amplifier. Well, once the output stage was fine, and we knew it was operational, and we'd also set the bias, if you, for example, changed an input source, what you could hear on the left-hand channel with no audio was a thud, okay? And it sounds almost like a thump. I think that's probably the best way. Just go, and that's what you hear. But on the right channel, nothing at all. On the left channel, then you could hear it, okay? And the reason for the noise is if you then measured across the speaker terminal, so this is no speakers connected, just the terminals at the rear of the amplifier, and you select, for example, from the front A or B, what you could measure is a high DC offset, but it wasn't high enough to trip the protection circuit. Normally with most amplifiers, if it sort of exceeds 1 volt, it'll trip protection, but this was slightly under, probably about 900 millivolts on the left channel and about 480 millivolts on the right channel, and that is a lot of excess DC offset that you read in there, and that was the issue. Now, for some amplifiers, and again it depends on make and model, some amplifiers will provide an adjustment to eliminate DC offset. Other amplifiers will use what we could term as a servo circuit, so the circuit will monitor the level of DC on the output speaker terminals, and then via the feedback network, a servo system, it will continuously correct for that and try and reduce it down to a minimum level. And it depends on the make and model of the amplifier. Now, some people may attempt on the ones where you can adjust it to get it down, for example, to 0 millivolts, you know. But in theory, to try and do that, it's not always possible, but for sure you don't want to have a DC offset in the area of 500 millivolts or even 900 millivolts. Now, when you're doing fault finding and repair, you may, if you were doing this amplifier, feel that actually I've repaired the channel, left channel, so there now must be an issue with the output stage of the amplifier that's causing the DC offset, and that's not true, okay? And it's not uncommon to go looking in there if maybe you've not seen this type of fault before or it's unfamiliar to you. But don't spend time going into the output or the driver stage of the amplifier looking for this DC offset. Now, when I talk about DC offset, I'm talking about something less than 1 volt. DC offset could be full rail potential if the output stage was short circuit. That's not what we're talking about here. We're talking about DC offset enough to create that thump, and I've seen it, you know, and I've been contacted via my YouTube channel where people have asked that and said, look, you know, when I sort of change an input, I hear this thud in the speakers, and that's why. So if you took your multimeter and you measure it across, as I said, you can measure what is the DC offset, and then for people who are probably unfamiliar with the term, what does it simply mean? Well, a DC offset can be both positive or negative. And if you had your sort of oscilloscope and you were measuring maybe a 1 kilohertz sine wave, ideally referenced to 0, if your peak-to-peak signal value was, say, 50 millivolts, then 25 millivolts would be below the 0 volt line, the negative part of that waveform, and then 25 millivolts would be above. But what happens is the DC offset then has the effect of moving it up or down with reference to that line then. So DC offset is the last thing that you want. Now, what I'm showing you here are 2 extracts from the service manual, and what I've done is I've just spliced between the 2. So if you look, you can see that the bottom part, that circuit diagram there, is for the right channel of the amplifier, and then the one above it, logically, is the left channel. And the components that I'm pointing to here, if you have a amplifier which typically uses this type of design, it is not uncommon to see this type of circuit design, and this is what we call long tail pair. Okay, so that means that the same transistors here Q301 and Q303 for the left channel are the same transistors, and then you can see that the emitter connection is common, so we call them a long tail pair. And you also do it like for impedance matching as well, but ideally that these gain of these components should be the same. But what has happened is, for whatever reason, these transistors over time have shifted, and the net result then is, instead of these transistors effectively being balanced, they're not. And this is what created this large DC offset on the left channel, and then the same again then on the right channel. So even if you took the components out and you put them on your meter, you're not going to, for example, see anything, and say, okay, well, that's definitely the fault. All that you do here is you just replace the transistors. So what I do is I just take the spare transistors from my component trays, and then I'll just put them on to the component tester, and I'll try and match the HFE or the gain of the two transistors so they're pretty much the same. On real high spec amplifiers, that type of arrangement is not uncommon, but what they do is they will encapsulate them with some form of conductive thermal compound, and then they will seal them then. So the two transistors are almost like back to back. Thermally they're at the same temperature to provide stability, and that is a normal arrangement. Here, this is a low cost amplifier, so you don't do it. And then what I'm showing next is the components actually on the circuit board, so you can see the left channel and then also then the right channel as well. So don't waste time doing all this sort of measurement once you took the components out. As engineers, we often use the term just block change. So you just replace the 4 transistors, and then once those transistors were replaced, powering the amplifier back up again, and you measure across the left channel, and the DC offset now was down to about 2.3 millivolts, almost insignificant. And then when you then check the right channel, 2.4, 2.6, which is perfect. So really insight, for people who are seeing this fault in terms of DC offset, it will save you a huge amount of time. And this is common, right? This isn't, something that happens very, very occasionally. I've seen this fault multiple times in different makes and models of amplifier, and all that you can do here, as I say, is just then to do the block change out then. So overall, I would say for this amplifier, quite interesting amplifier repair. The fact that it's in 2 parts, but I think also as well what it does highlight is you may repair an amplifier, but then when you get to the test phase of the repair, where you check in to make sure that it's operating correctly, it is not unusual to find another fault, and that's what you see here. So you're kind of getting 2 repair tutorials in the one sort of video, which is good, but it also gives you insight, to the real world of electronic repair. Sometimes it can be a little bit frustrating, I've got to be honest, when you sort of reassemble the amplifiers, and then you go to test phase, and then you then find a secondary issue. Now with this amp, I've sort of changed slightly with regard to how we sort of detected the DC offset. It wasn't a case where I reassembled the amplifier, connected speakers, and then I found the DC offset. Remember, what happens is you repair the output stage, and then you're then checking them for the DC offset, before you would be connecting your speakers then to the amp. So there you have it. So quite an interesting repair, as I say, and I do appreciate you stopping by and listening to this repair tutorial. And if you have any questions or you need any information, by all means email audioamplifierservicing@aol.com, and I'll be happy then to respond back to you and provide any guidance or support. So all the best to you till the next time. Cheers, bye bye.